great afternoon for you. I think the morning went fantastic as well. Our next speaker is Stephen Swanson. He is a professor at University of California in San Diego. So when I was talking about starting rocket engines at 455 degrees below zero, he probably has no idea what that's all about. Somebody, or even starting your car engine at, what do they say, at 0, minus 20, or minus 40. He was thinking, what does that even mean? So, but anyway, Stephen is running a project, or going to represent a project called NOVA, which he claims is the file system, the fastest file system in the universe for persistent memory for NVDIMMs. So, Stephen, looking forward to hearing what you have to say.
Thank you very much for the introduction. I should say, I'm sure there's some aliens somewhere that have some very fast file systems, but I don't want to make claims I can't support. So I run a research group at UCSC. We've been around since about 2008, my research group, and we've studied all kinds of different aspects of non-volatile memories, ranging from flash and conventional SSDs, and now we're doing a lot of work looking at non-volatile main memory technologies like NVDIMMs and so forth. So today I'm going to tell you about a file system that we've built over the last 18 months or so called NOVA. And NOVA is the result of an effort to really rethink the way that people design file systems to take full advantage of these non-volatile main memory technologies that we're all here to hear about today. And what we've seen is that the result is that we can build file systems that look very, very different than conventional file systems, have much better performance than existing file systems, and also have much nicer properties from a usability and programmability perspective than existing file systems. So if we look at sort of the oh no.
No screen.
All right. There we go. All right. So if we look at kind of how we've ended up where we are with respect to file systems in the world, there's a lot of file systems available. These are all the kind of most popular file systems in Linux right now. And they were designed and sort of grew up running on hard drives and on SSDs. And so they've been designed from the very beginning to kind of, I guess, partly take advantage and also partly just cope with the performance characteristics of this kind of media. And first we had hard drives, of course, and lately we've had SSDs. And we've had new file systems for SSDs that are optimized in slightly different ways. But they're very much kind of wedded to the hardware on which they were designed. And one of the consequences of this is that the file system designers have made a lot of trade-offs. In particular, they've made trade-offs about the kind of semantics that these file systems provide. So this is data from a paper from a group at the University of Wisconsin in Madison. And what they did is they took a bunch of different file systems, disk and SSD-based file systems, and they went in and did some experiments and identified places where those file systems didn't deliver the kind of atomicity guarantees that the POSIX standard requires. So things like, can you do an atomic single-sector overwrite? Can you do an atomic single-sector append? Can you do multi-sector overwrites atomically and things like this? The checkboxes are where the file systems provide that kind of atomicity. And the gray boxes are places where those file systems fail to provide that kind of atomicity. So the two best options are exe4 with data journaling, which is sort of the most hardened version of exe4, and ButterFS. And they do pretty well, except not even those two file systems can do an atomic n-block overwrite. So the consequence, there's two consequences of this. The first is that by making these kind of compromises, the designers of these file systems are able to increase performance. The other consequence, though, is that this actually makes these file systems pretty difficult to use. If I'm a database developer and I care a great deal about how my data is stored and that it be stored correctly and consistently, then I actually, first of all, I have a challenging programming problem because some things are atomic and some are not. And the second is that I really need to be programming for a specific file system, right? I need to be targeting, exe4 with data journaling or ButterFS And if I want to target XFS or Erasure FS, I have to deal with a slightly different set of problems. I have to test a slightly different set of configurations. It just makes the programming problem harder. This is sort of the problem with existing file systems from a programmer's perspective. Now lately, as these persistent memories have kind of come onto the scene, people have started developing specialized file systems for those. The first one that I'm aware of was a proposal called BPFS back in, I think, 2009 from Microsoft Research. There have been some other research proposals as well. DMFS was the first file system from Intel, which has now been deprecated. And then it's also begun to find its way into more mainstream file systems. So there's a version of ext4 that supports DAX, runs well in non-volatile main memory, and a version of XFS that also runs well in non-volatile main memory. And then there are a set of file systems that have been a little more recent, have been built from the ground up for non-volatile main memory. And those include Nova, which I'm going to talk about today, and N1FS, which is the file system. And these are really built from the ground up to run on these new memory technologies. Now, even these file systems, at least other than Nova, that I have listed here, also don't provide all of the atomicity and consistency guarantees we would like. BPFS does a pretty good job, but all the other ones that we've tested fail to provide good data atomicity. So they do metadata pretty well, but they don't protect your data with strongly consistent updates. So our goal with Nova, this is a little out of order. So there's also some performance disadvantages of the kind of legacy file systems as they've been ported to take advantage of non-volatile main memory. So ext4 with DAX doesn't provide data atomicity support. There's no ext4 data journaling and version that provides both data journaling and DAX support. There's a single journal that's shared by all file accesses, which is the point of can be a bottleneck in performance. As we'll see, it leads to relatively poor performance on non-volatile main memory. And we heard a little bit of this earlier from Andy, is that the folks that maintain this file system and also XFS, those file systems are still disk file systems, and obviously we need them to remain disk file systems. And so the development teams are kind of hesitant to make significant changes that would benefit non-volatile main memory operation over conventional operation. And Andy mentioned this problem with doing fast msync. And so there's some kind of a variety of issues that are going to keep these file systems from getting to the level of performance that we would like to have. So the goal of Nova is to provide all of these strong atomicity guarantees. So we provide all the kinds of atomicity that POSIX requires. And at the same time, provide very high performance. So how are we going to go about doing that? So the first thing we're going to do is we're going to dispense with all the disk-centric kind of baggage that comes with existing file systems. We're going to provide strong consistency guarantees. So we're not going to make any of those sacrifices to improve performance because we're not going to need them. We're going to make it as lean and as fast as possible. So the code base is pretty small. And we try to do our best to make sure that all the paths are fast paths. We're able to freely optimize for NVDIMMs. There's no reason for us to worry about what some future disk-based or block-based storage system might want. And so, for instance, we can do user space fsync and msync without any problem. And we can focus very heavily on the latency and bandwidth advantages that NVDIMMs provide and optimize for those very specifically. So, for instance, take advantage of the fact that we can do, say, 64-bit atomic writes to the NVDIMMs. The other thing that we wanted was for it to be freely available. In the best world, this would end up integrated into Linux, and that means it needs to be GPL. And so all the source code for Nova is freely available online on GitHub, and we've had people from lots of different companies download and try it out. So how does Nova work? So in the past, there have been basically 3 different ways that file systems have worked. They've either been journal-based, like ext4. They've been shadow paging-based, like XFS. Or they've been log-based, like a lot of the flash-based file systems. So what's been really interesting about Nova is that as we were engineering it, we found that we could combine aspects of all 3 of those different kinds of file systems, kind of take the best of each of them to build what is kind of a completely new style of file system. So how is Nova log structured? So Nova, kind of the basic unit of providing consistent updates is the log. But rather than provide one log for the entire file system, Nova actually provides one log for each inode in the file system. So every file has its own log. That allows for massive concurrency, which NVDIMMs are very good at providing. The logs are also non-contiguous. There's no reason for them to be laid out sequentially in memory. So that makes memory management easier. The logs, of course, provide a very fast, simple mechanism for doing atomic updates. The other thing that's a little bit different about our logs is that they only include metadata. There's no file data in any of our logs. That keeps the logs small and also simplifies memory management for file data that I'll talk about in just a moment. So the way this works is we have a log. We have a pointer, and each inode data structure has a pointer to the tail of the log. If you want to add something to the log, we write the data at the end of the log, and then we can do an atomic update to that tail pointer to atomically add that log entry. So Nova is also copy on write. We use copy on write for file data. If we want to do multi-page atomic updates, the way that works, we have a file here. We have its log that has some metadata entries that point to the pages, the data pages for that file. We want to add, or we want to do a multi-block write. We write some new data to an empty page, or a couple of empty pages, and then we use the same trick to append a new metadata entry to our log that atomically adds those two data pages to our file. Now, what's nice about this, compared to conventional log structured file systems where we have to do a complicated cleaning operation to recover the old version of data 1, is we can now instantly recover that data and put it back in the free folder because that data doesn't live in the logs. We don't need to do the log cleaning bit. And then finally, for complicated metadata operations that involve multiple inodes, we use very small fixed-size journals. So for instance here, if we want to, say, add a file to a directory, we can append data to the log for the directory, append data to the log for the file, and then we use a journal to atomically update both of those tail pointers at the same time. And so that lets us do things like moving a file from one directory to another, also atomically. So the result of this, we have a file system that looks unlike any file system that has come before it. It has some really nice performance properties I'll talk about in a minute. But one question that turned out to be very interesting in both file systems for non-volatile main memory, but also just in some of the questions about programming models and libraries that we've heard about, is how we're going to deal with errors. So there's lots of different errors that can occur. We'd like our file system to be robust to as many of them as we can. So we can have media errors that can either be hard errors or soft errors, whether or not a cell permanently breaks or just returns the wrong bit sometimes. There can be local system failures where maybe a DIMM goes bad. We can also have larger scale failures where maybe we lose an entire system. So Nova includes reliability mechanisms that are going to address a bunch of these error cases. This is going to come out in our April release. We're kind of working on this right now. So what we're going to do is we're going to replicate all the metadata of the file system. So we'll have two copies. If we detect a media error in one, we can copy the good version over to restore that data. We're going to add CRCs to all of our metadata structures so we can detect corruption either from kind of errant writes or stores to memory, as well as any other memory errors that we aren't able to detect using ECC. We're going to use erasure codes for file data so that we'll be able to recover from errors in file data. And then we also have support for read-only checkpoints, so you can take checkpoints anywhere along the way in the file system, and you can use that to do backups and so forth, which is also critical for deployment in the enterprise space. The other thing we're going to add, which kind of hurts my heart a little bit, but the Linux folks said it would be a really good idea, is we're going to have unsafe modes that give up all the consistency guarantees to get better performance, because apparently some people just don't care about their data. They want to go really fast. So that's fine. We can, when we run performance numbers, compared on some operations are actually slower than ext4 DAX because ext4 DAX, they apparently don't care about their data, so they're able to go faster. So we'll be able to beat them in those cases as well. So I have a couple of performance measurements. So this is basic operation latency. We're going to compare to ext4 with data journaling and ext4 DAX. We compared two versions of ext4 because neither one of them actually provides everything that Nova does. ext4 journaling provides strong consistency guarantees, almost as strong as what Nova provides, but it's not DAX. And ext4 DAX is DAX, but it doesn't provide the strong consistency. And then we have M1FS in purple and then Nova in green. And so you see we're faster than conventional file systems that have been adapted for DAX operation by a good bit, and we're a smidge faster than M1FS as well. And then on larger scale workloads, this is some file bench workloads showing throughput. We are a lot faster than, much better throughput than existing disk or SSD-based file systems. And we're basically neck and neck with M1FS. So we get very, very good performance. We have much stronger consistency. And so all around that kind of gets us to where we want to be with our file systems. Easy to program, highly reliable, and also very, very fast. So to wrap things up, I'll leave some time for questions. So existing file systems don't meet the needs or the requirements of applications on NVDIMM file systems, right? We're going to buy this new memory. It's going to be, it's going to be cheaper per bit than DRAM, but more expensive than SSD. So we want to get the most kind of performance bang for our buck that we can. Nova's multi-log design achieves high concurrency, efficient garbage collection, and fast recovery. I haven't talked much about the garbage collection story or the fast recovery piece, but basically we're able to exploit all the parallelism in modern machines when we're doing recovery and all the bandwidth and concurrency that our multi-log structure provides to recover very, very quickly if there's some corruption that happens when the file system is offline. Nova outperforms existing file systems by providing stronger consistency and atomicity guarantees, which makes it easier to program. And Nova protects against data, against media errors and system failures with a suite of different techniques. So I'd like to wrap up by thanking all my graduate students who actually do all the hard work, as well as Intel and Micron, who have been very supportive in kind of explaining things like the error model for what's, how errors are going to show up in systems. I definitely encourage you to go and try Nova. Here it is on GitHub. It's freely available, totally GPL. We have lots of people download it and try it out. It seems to work really well on a wide variety of systems. If you have any trouble, definitely send us an email. We're very eager to have people trying it out and telling us where it works well and where it doesn't. And that's it. I'm happy to take any questions.
We'll start with Tom. Give Tom first priority because. Thanks, Chip. You made a huge contribution to be here today.
Steve, I was very surprised to see you mention erasure coding. Are you calculating it on the fly? But more importantly, why do you need it? Do you really expect that many devices to be involved that erasure coding is the approach for?
So the approach we're going to take to erasure coding. So if I'm reading a page of data on one of these NVDIMMs, and I get an uncorrectable ECC error, I'm going to lose some area of data that Andy refers to as the blast radius, a very colorful metaphor. So I lose the blast radius worth of data, and that comes back poisoned to the CPU. So in order to recover from that kind of error, we're going to store in a separate region of NVM. We're going to store erasure code data, basically kind of RAID 5 style parity, so that we can recover that piece.
Very simple erasure.
Very simple erasure code.
Okay.
RAID 5, maybe RAID 6.
Okay.
Yeah.
Okay. And I mean the number of devices. So you're just going to have another copy of it nearby.
So this is a really interesting and hard question that we have not tackled in detail, right? So the way that physical addresses are mapped onto DIMMs, the way that even addresses inside a DIMM are arranged onto banks, like all of this has implications for kind of what the failure domains are. And there's going to be sort of intersecting failure domains with rows and columns and banks and all this stuff. So the way that we've been thinking about it in Nova is that it's pretty easy for us to specify kind of different pools of pages that we can draw from. And so we can ask one allocator for the kind of primary replica of a piece of metadata, and another allocator for another version of that same piece of metadata. And then once we kind of figure out all these error domains, we can point those different allocators at different kind of independent regions. It could be on different DIMMs, it could be on different banks. We can figure out how exactly that should go. It'll probably vary, right, depending on the architecture of the memory and so forth. And then we should be able to separate the replicas so that we don't get kind of fake sharing between them. But my impression is that this mapping is pretty complicated. I think it's solvable, but I'm not sure that we're the right people to go through and do the detailed work of solving it. I'll leave that in.
Hi, I'm Ace from Plexistore. Great survey. I have two unrelated questions. The first kind of continues the Erasure coding question. So the log structure and Erasure coding, that kind of gets into the way of DAX. And I wanted to know if you have any plans for DAX or what.
Yeah, so we support DAX. The log structuring thing is not a problem because our data doesn't live in the log. So the data itself is not log structured, so you just modify the data pages directly. The erasure coding thing is harder, right? So this is actually a conversation that we've been having internally, trying to work through what exactly the kind of semantics are. I think one alternative is that there'll be a mode, and maybe you turn off the erasure coding when you do DAX. Maybe you sort of scrub in the background. Maybe you do it when you do MSync to guarantee that when you come back, you should find the right kind of data. There's a couple different options there. I think a really, the promise of DAX, right, is that the overhead is zero. And the only way to get zero cost ECC is to do it in hardware somewhere. So that might be where we end up eventually, and maybe eventually, Intel or someone else will provide support for doing that kind of in hardware, and then we can have a flag or something to turn on.
So the second question is unrelated. In terms of integrity checks, so when you're working with a traditional block-based file system, you use block devices. They have DM flaky and all those mechanisms to basically simulate errors.
Yeah.
I was just wondering how you check for those types of things.
Yeah, so that's also a challenge. So we've been thinking about a couple different ways. There's some mechanisms for injecting errors inside Linux. The problem is it's very hard to inject a non-correctable ECC error in a realistic way. So one possibility is to use virtualization somehow. I imagine that a virtual hypervisor could do that and get the right code path to be triggered. So that's kind of what we're looking at right now, but this is a challenge. It would be nice if we could set a debug register somewhere that's the next time you access this cache line, just fail, and then we could agree with that. Yeah.
Okay, one last question.
So, okay, it's actually two comments and one question, but they're brief.
One question, please. We have to stay.
Okay, are the logs themselves files in the file system?
No.
I'm going to say that is a very bad architectural decision, because that means that the policies and algorithms and code for flushing file data cannot be applied to the logs. And high-grade commercial file systems like Veritas VXFS make everything a file. The inodes are in a file, the transaction log is in a file, especially since you don't have disk latencies. I absolutely don't see the point of having multiple log files or multiple inode files.
So I think the short answer to that is that there's no value in reusing the flushing mechanism because there's no flushing mechanism.
Well, there are a number of file system developers in this audience, and we can take this offline.
All right. I was hoping to get back.
So most of Stephen, I assume if more people want to talk offline, you could meet in the back after this.
That sounds fantastic. I love it.
Okay, so keep the debate going. Stephen, thank you very much. It's great to have some people doing it here as well.